All right, welcome back, guys. So we're gonna continue lesson 4.1 from where we left off. The next thing we have is another definitions, which we've already know this definitions or familiar with this definition. Um, let's go ahead and define this next definitions here. Okay, all right. So given a function, so let's say we say that C is a critical value. We say that C is a critical value if the function derivative evaluate C, the output is 0. We've already done this a lot before this section here. And then or f prime of C itself does not exist. So this would be a new part here. Okay. So we define a value C in the domain, or could be not in the domain, to be a critical value. Critical value, that C is a critical value. If we evaluate the derivative and we get 0, or the derivative does not exist at that value C. So those conditions will make the value of C being the critical value. So let's go ahead and take a minute and kind of demonstrate that from the function that we start out in this lesson here, and that was this function here. Okay, so let's go ahead and do that. So quick example. Okay, maybe I used this right here. So if f of x is x to the third minus 3x, then that means f prime of x is 3x squared minus 3. Let's go ahead and solve this, where that would be equal to 0. Okay, notice that if I divide both sides by 3, I get just x squared minus 1 there. And I can factor using difference of square. So that gives me x equal to 1, x equal to negative 1. So these are my C value. Why? Because when I evaluate the function at these values, the derivatives is 0. Okay, so we've done that prior to this lesson. Solve the derivative when the derivative equals 0. So in another word, what we consider this before this is that those are the values of x such that the actually, I want to say this. Those are the value of x makes or gives. Okay, I want to go ahead and do this here. X gives the horizontal tangent line, and that's what we were. What was that? That's the language that we used prior to this lesson here. So let's go back to the graph. So what does that mean in terms of the graph here? All right, let's see if I can copy. Actually, can I copy this here? Can I copy this graph again? And then paste it down here. Oh, well, I don't want to do that. So let's go back to the graph itself here. Maybe I can do a highlight here. So in this graph, in this function, the two critical values are the 1 and the negative 1. Okay, at those values, the derivative is 0. You see that horizontal tangent line. Okay, and let's discuss what happened to the left of that value, to the right of that value. Okay, so let's look at to the left of that value. So to the left of negative 1, the slopes of tangent line, f prime of x, is positive. Okay, so it's going up positive. And to the right of that critical value, negative 1, the slope of tangent line are negative, it's decreasing. Okay, and then in between that, well, at negative 1, we have this flat line here. First example, we discussed this concept. What does that mean? That means at this point here, we will consider this value here. That is what? Maximum value, right? Where you say that, okay? And down here where you say this is the minimum value. Turns out a function can have multiple maximum value or minimum values. We call those a local extrema, okay? So let's go ahead and define the next definition as well, okay? Definition. Local extrema. Okay. And you know what? I'm going to go ahead and do this through a kind of not written down, but in terms of the diagram. Okay. So we say that, so the sign, local extrema sign charts, let's go sign charts. Okay. So suppose we have the horizontal axis. Imagine this is my x and this is my critical value. Okay. And then let's say this is the interval we're looking at. So if my derivatives, if my f prime of x are negative, negative, negative to the left of the critical value, and then positive, positive, positive to the right of the critical values. Okay. If we have this scenario here, we say that f of x obtains a local, in this case, so that'd be negative, a local minimum at C. Okay, so that example is kind of like this. See, it's kind of like, so what does this mean? It's kind of like this here. Here's your C, so it's kind of like decreasing, so let's say decreasing and then increasing, kind of like that. So this is your C there. So negative slope on the left, positive slope on the right. Okay. And then if we have a scenario where the f prime of x is positive on the left side of C and negative on the right side of C, then in this case here, f of x obtains or has a local maximum at C. Okay, so in this scenario, it's kind of like this. Here we have increase in tangent slope on the left. Once it hits C at 0, and then decrease again. So in this case, this is the maximum, the local maximum. And a function can have multiple of these, and so that's what we call them local. Let's also throw in the function value itself as well. Let me use green. Okay, if we combine the function values. Okay, let's see if I can squeeze in here. Let's go ahead and do f of x right there, f of x right there. Let's zoom in. So this is saying that if the derivative, okay, if the derivative is 0 or not 0, less than 0, the slope of tangent line is less than 0, then to the left of that critical value, the function value f of x is decreasing. Okay, and that's what we discussed in the first video. And the slope of the tangent line is positive, that means increasing. Okay, so for a local minimum to occur at C, we have function value go from decreasing to increasing. And then similarly, for a local maximum occur at the critical value C, the function values goes from increasing, right, increasing to decreasing. Okay. All right. So what we have so far here, we have critical value definition, we have local extrema definitions, and I think we're ready to do an example, kind of tie all this thing together here. So let me go ahead and end this video and I'll start example in the next